Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the grand tapestry of human intellectual achievement, certain threads possess a brightness and strength that reorder the entire pattern. Isaac Newton's 1687 masterwork, the Philosophiae Naturalis Principia Mathematica, is such a thread. It represents a singular watershed, a moment when the disjointed inquiries into motion, astronomy, and mathematics converged into a coherent and universal system of breathtaking power. The work did far more than solve outstanding problems. It established a new paradigm for scientific inquiry itself, one founded on the indissoluble union of empirical evidence and mathematical deduction. The Principia achieved its monumental status by forging a revolutionary synthesis of rigorous mathematical proof, precise observation, and a potent philosophical framework. This synthesis created a unified science of mechanics that governed both the fall of an apple and the orbit of a planet, establishing the foundational principles of physics that would reign for over 2 centuries. To comprehend its impact is to examine the intellectual landscape Newton inherited, to dissect the magnificent architecture of the work itself, to trace its immediate and enduring influence, and to appreciate the profound scientific and philosophical debates it ignited across Europe and beyond. The world of natural philosophy before the Principia was a realm of brilliant yet fragmented insights. The heavens and the earth remained governed by separate principles. Johannes Kepler, through heroic computational effort, had derived his 3 laws of planetary motion, describing with uncanny accuracy the elliptical paths of the planets and the mathematical relationships governing their speeds. His work was a triumph of descriptive kinematics, a magnificent account of how the planets moved, yet it remained silent on the essential question of why. What physical cause compelled a planet to sweep out equal areas in equal times or to follow an ellipse with the sun at one focus? The answer was absent. In the terrestrial sphere, Galileo Galilei had laid the groundwork for a science of dynamics. His experiments with inclined planes and his thought experiments on projectile motion had yielded profound truths about inertia and uniform acceleration. He had shown that the laws of motion on Earth were mathematical and predictable. His physics, however, stopped at the Earth's surface, leaving the celestial machinery untouched. The most ambitious attempt at a unified cosmology came from René Descartes, whose Principia Philosophiae of 1644 proposed a universe filled with swirling vortices of ethereal matter. In his purely mechanistic system, contact action was the only permissible mode of interaction. Planets were swept along by these cosmic whirlpools, and gravity was a consequence of their pressure. Descartes offered a complete, qualitative vision, a universe without voids or mysterious long-range forces. This Cartesian model was intellectually satisfying to many and became the reigning orthodoxy, particularly on the continent. Yet, its explanatory power was superficial. It struggled to account for the precise mathematical relationships discovered by Kepler and remained a system of grand philosophical conjecture, with weak quantitative support. The central challenge for natural philosophy, therefore, was to bridge this chasm, to find a single, universal, and mathematically precise dynamic principle that could derive Kepler's celestial laws as a necessary consequence and show them to be one and the same with Galileo's terrestrial mechanics. Newton's Principia was the direct and decisive answer to this challenge. The formal architecture of the Principia is a testament to Newton's ambition to construct a science with the certainty of geometry. He self-consciously modelled his work on Euclid's Elements, building an imposing logical edifice upon a foundation of definitions and axioms. The opening definitions immediately establish a radical conceptual framework. Here, Newton posits the existence of absolute, true, and mathematical time, which of itself, and from its own nature, flows equably without relation to anything external. He likewise defines absolute space, which in its own nature, without relation to anything external, remains always similar and immovable. This absolute spatio-temporal stage was a profound metaphysical commitment, providing a fixed, universal container within which all motion could be unambiguously measured. He then defines quantity of matter, or mass, as arising from its density and bulk conjointly, a fundamental property of a body distinct from its weight. Upon this foundation, Newton erects his 3 axioms, or laws of motion. The first law, the principle of inertia, refines the work of Galileo and Descartes, stating that a body remains in its state of rest or of uniform motion in a straight line unless acted upon by an external force. The third law, concerning action and reaction, posits that for every action there is an equal and opposite reaction, a principle essential for analysing systems of interacting bodies and ensuring the conservation of momentum. It is the second law, however, that forms the dynamic heart of the entire system. Newton formulated it by stating that the change in motion, what we now call momentum, is proportional to the motive force impressed and occurs in the direction of that force. In modern language, this establishes the fundamental relationship that force equals the time rate of change of momentum for a constant mass. This simplifies to the famous expression F equals ma, or force equals mass times acceleration. Here, for the first time, was a precise quantitative link between a cause, force, and its effect, a change in motion. These laws were presented as universal axioms, from which a complete science of mechanics could be deduced with mathematical certainty. With this axiomatic machinery established, the Principia unfolds in 3 monumental books. Book I, The Motion of Bodies, is a purely mathematical treatise, a stunning display of geometrical power. Working in the classical style of Apollonius, Newton masterfully conceals his newly developed method of fluxions, what we call calculus, behind a screen of intricate geometrical proofs involving the ratios of vanishing quantities. The book's central achievement is its analysis of motion under central forces. In Proposition 11, Newton provides the spectacular proof that if a body orbits a central point under the influence of a force that varies inversely as the square of the distance, its path must be a conic section, an ellipse, a parabola, or a hyperbola. In one deductive step, he had derived Kepler's first law of elliptical orbits from a physical principle, revealing the dynamical cause behind the observed kinematics. This was the intellectual core of the entire work, the mathematical engine that would drive the cosmic explanation. Book then, The Motion of Bodies in Resisting Mediums, serves a strategic purpose. It is a systematic and devastating demolition of the Cartesian vortex theory. Through a series of rigorous mathematical arguments, Newton demonstrates that the motion of bodies within a fluid vortex is utterly inconsistent with Kepler's laws. A planet swimming through a Cartesian ether, he showed, would be slowed in a manner contrary to observation, and the orbital periods would fail to match the required proportions. Book who thus clears the intellectual field, exposing the reigning cosmology as mathematically untenable and paving the way for his own alternative. Book The System of the World, is the grand synthesis where the mathematical principles are finally applied to the physical cosmos. Here, Newton marshals astronomical data to show that a single force, which he calls universal gravitation, governs the entire solar system. He demonstrates that the force holding the moon in its orbit around the Earth is the same force that causes an apple to fall, its strength diminishing precisely with the square of the distance. He then extends this principle to the Sun and all the planets, proving that the force of gravity is proportional to the product of the two masses and inversely proportional to the square of the distance between their centres. This single law, applied with the mathematical tools of Book I, yielded a cascade of explanations for previously intractable mysteries. It accounted for the orbits of comets, transforming them from unpredictable omens into law-abiding members of the solar system. It explained the tides as the result of the differential gravitational poles of the Moon and Sun on the Earth's oceans. It accounted for the slight precession of the equinoxes, a slow wobble in Earth's axis, as a consequence of the Moon's pull on Earth's equatorial bulge. The Principia presented a universe unified under one set of mathematical laws, its phenomena predictable and its structure comprehensible. The reaction to the Principia was one of profound awe mixed with considerable confusion. Its mathematical density was formidable, leading to the famous quote that Newton was a man who wrote a book that neither he nor anyone else could understand. While its immediate readership was small, its impact was seismic. In Britain, Newton was elevated to the status of a national hero, his work seen as the ultimate triumph of the scientific revolution. On the continent, however, reception was far more critical, centered on the philosophical implications of his central concept, the idea of gravity as a force acting instantaneously across the vast emptiness of space. An action at a distance struck thinkers like Gottfried Wilhelm Leibniz and Christian Huygens as a relapse into the occult qualities of scholastic philosophy. It seemed unmechanistic and unphilosophical. Descartes' universe, for all its empirical flaws, had at least provided a tangible, contact-based explanation for celestial motion. In contrast, Newton's gravity was a mysterious force whose ultimate cause he famously refused to speculate upon. His declaration, "Hypotheses non fingo or I frame no hypotheses," was a seminal statement of scientific positivism. Newton asserted that his task was to describe the mathematical law of gravity's effects with precision, as confirmed by observation, while leaving the question of its underlying nature to future inquiry. He provided the quod, the what, and the quantum, the how much, but he left the quomodo, the by what means. Over the following century, this Newtonian framework became the bedrock of physical science. Mathematicians like Leonhard Euler, Joseph Louis Lagrange, and Pierre-Simon Laplace embraced Newton's laws but recast them in the more powerful and flexible language of analytic calculus, stripping away the cumbersome geometric scaffolding to reveal the elegant algebraic core. Lagrange's 1788 Mécanique analytique stands as the ultimate fulfillment of this program, a work he boasted contained no figures at all. Furthermore, the Principia's vision of a rational, ordered, law-governed universe provided the primary intellectual fuel for the Enlightenment. Philosophers saw in Newton's success a model for applying reason to all domains of human life, from government to morality, hoping to discover their own underlying natural laws. Though Einstein's theory of general relativity would eventually supersede Newtonian gravity in regimes of extreme speed and mass, the Principia's laws remain astonishingly accurate for the vast majority of engineering and astrophysical applications. The system it created continues to be the foundation upon which classical mechanics is taught and practiced. In conclusion, the Philosophiae Naturalis Principia Mathematica stands as more than a book. It is a monument to the power of human reason to decode the universe. Newton's genius lay not merely in his individual discoveries, but in his grand architectural synthesis. He took the empirical regularities of Kepler, the terrestrial dynamics of Galileo, the axiomatic method of Euclid, and his own powerful invention of the calculus, and from these elements he constructed a unified and universal science. The work provided a definitive refutation of the qualitative, speculative cosmology of Descartes and replaced it with a system of quantitative prediction and rigorous mathematical proof. By unifying the terrestrial and celestial realms under a single law of universal gravitation, Newton erased a distinction that had plagued natural philosophy since antiquity. The universe it revealed was a place of profound order and mathematical elegance, a clockwork system whose intricate movements could be understood and predicted through the application of a few fundamental principles, while the silent, invisible force of gravity it posited would provoke a century of noisy debate. The methodology it enshrined, a powerful dialectic between mathematical theory and empirical verification, became the very definition of modern physical science. The Principia forever altered our conception of the cosmos and our confidence in our ability to comprehend it, leaving a legacy written not just in ink, but in the very motions of the stars.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.